Today, the first speaker is Xuhua He, who will talk about Cocenters of Hecke algebras and categories.
Thank you very much. Yeah, it's my pleasure to come to the ICBS and to give a talk. And so I'm a student of George Lustig, and also today I'm going to talk about what I learned from him. Okay, so let's start with some general philosophy. Well, I mean, so yesterday I have this is a math night, and actually people actually talk about what actually attract them to a particular field. So to me, what actually attracts me most into this Lie theory is that there is a very deep and profound connection between the continuous symmetries. I mean, for example, the GOM, and the discrete symmetries, for example, the SN. And so they actually from the various aspects, we can do it algebraically, and combinatorially, and geometrically. And so this actually due to the pioneer work of Lustig and others, and starting from the 70s and 80s, and this actually gives rise to what nowadays we call the geometrical representation theory, and which is actually a very interesting area. But actually, I would like to start talking about this is a connection between the continuous symmetry and the discrete symmetry by we call the Tits philosophy from the 1957, where he basically says that the wire group of the Lie group can be interpreted as the group of the F1 rational points. Well, so F1 is the field of one element, and this actually tells that actually, for example, the Sn is not just a finite group, but there's actually many deep structures behind it. And a very famous example, and which I call this is the algebra combinatorics geometry combined all together. So I have this is the three columns, and say the combinatorics, algebra, and geometry. So combinatorics, we can start with the wire group, for example, the Sn. And so if you actually do the deformations of the group algebra, what you get is a Hecke algebra. And so what actually reveals actually in the geometry, this is the Schubert varieties, the BWB, quotient by B in the flag variety, so indexed by the wire group elements. There is actually I would say that actually probably the one of the most important theory in representation theory. This is the Cocenters theory. And so left-hand side combinatorics, we say this is the Cocenters polynomials. The PYW corresponds to the two elements in the wire group, y less than or equal to W. And in the algebra, we actually have this is a Cocenters basis. We actually restrict to a smaller part, the coefficient, we say the Cocenters polynomials. And the geometry, what it reveals is this singularities of the Schubert varieties. And the Cocenters theory, and something refer to this the Cocenters-Lustig conjecture, but in fact, in the two papers of the Cocenters-Lustig in the 79 and 80, they already proved half of the conjecture, and the rest half was proved independently by Belinsky-Bernstein, by Bernstein, and by Belinsky-Kashiwara. And later, Zogel started the categorification versions of this is the Cocenters theory, and this is actually finally settled by Elias and Williamson. And they actually have made further developments, which actually, so this actually relates the characters of the irreducible representation with the Verma modules. So what we're going to talk about today is something similar. Still, we want to say the combinatorics part, the algebra part, and the geometry. And so for this combinatorics part, we start with the affine wire group. I'm going to actually talk about it in details shortly later. From the affine wire group, if you do the deformation, what you get is the affine Hecke algebras, and the geometry is the affine Schubert varieties. So this is actually similar to what we have seen above. I mean, in fact, this actually works for any Casimudi groups, not only for the final wire groups. But what I'm interested in most is that what happens if you actually consider the conjugation action. So combinatorics, we just say, okay, we consider all this conjugation action. I denote this by W quotient by W. This actually means the conjugation action. And the algebraic version corresponds to this. This is actually the cocenters of the affine Hecke algebra. Well, for there's something interesting that there's no the direct analog in this geometrical part. However, we can actually go one step further. Go to this is what I call this as a GIT quotient. I just actually borrow the name the geometric invariant theory, and this is the double slash. This is the notation for this GIT quotient. And well, on the algebra, this is a decomposition of this cocenter into this is what I call this the Newton component, and the geometric part is this. We have this the Newton stratification, and I'm going to say actually why I'm interested in this and what is this actually good for, and then finally we're going to actually talk about some Whistle work together with Xinwen Zhu. And also my former postdoc Aaron Eliado. So towards the categorifications and well towards the conjectural capital shifts on the loop groups. Okay. First let's start with actually I suppose everybody knows this. This is the classifications of the semi-simple Lie groups. And as George said, and this is actually probably the most important paper. And starting from there, we have this is the Bourgeois decomposition. So we will start with a reductive group, and we fix the Barrère subgroup and its wire group. And well, what's important is this is not just a finite or discrete group. But actually, the two important features are the Bourgeois order, which actually reveals the geometry, the Creux relations, and the length function, which reveals the dimension. And so this is actually the example in the GLN. So one-dimensional contain the two-dimensional, and so on and so forth. So this is why we call this is the flag variety. And well, so the Bourgeois actually have this is the decomposition of this is the flag into this disjoint unions of the Schubert cells. Okay, I should modify that. Thank you. And so, in fact, from this we can actually see this is the teeth philosophy comes from. So, this theory actually works for any field. If you restrict to the finite field, and if you count the number of the points, then this is a finite flag. The number of points is equal to the summation of the Q to the length of W. And well, for the finite field, it does not make sense when Q equal to 1, but we artificially make the Q equal to 1. What we get to the left-hand side is just the I mean, this just says that the finite flag over the field of one element is just this is a while group. This is actually, I think it's probably one of the motivations for this teeth philosophy. Okay, so the Hecke algebra is the deformations of the group algebra, and this given by this is the generators and the relations. So it actually looks like the group multiplication, but if the length is additive, and otherwise for the simple reflection, the relation is s squared equal to 1, but we deform it. This is the ts plus 1 times the ts minus q equal to 1. And also, I just talk about this for the equal parameter case, and there is actually the more general versions for the unequal parameters. We can do something similar. And well, where does the Hecke algebra comes from? When q equal to 1, this is just the group algebra. When q is the power of the prime numbers, then this is just the endomorphisms of the functions on the flags. Well, so this is various cases for the while group. The first one is this is the finite G2, and the second one is this the affine G2, and so that one is actually this I forgot the name. So this is just this is a triangle with the infinity edges. Okay, well, so now let's actually come to the titles of my talk, the cocenter, and why we care about the cocenters. And still, actually, the motivation is actually very basic. I mean, in the first few classes, when you first study the Wepin tension theory, you know that for the finite group, the number of irreducible Wepin tension equal to the numbers of the conjugate classes. And well, we can actually reformulate this in a different way. So the left-hand side, this is actually the rank of the quotient group of a fine-dimensional Wepin tensions. And on the right-hand side, the number of the conjugate classes is equal to this the dimension of the cocenter. So cocenter by definition is this algebra. You quotient out its commutator. And one can check easily for the group algebra, then actually the two elements in the same conjugate class, they have the same image in the cocenter, and this actually form a natural basis. And well, how these two sides they actually are connected. So this actually is not only a numerical identity, but in fact this is what we call this is the capital tables, which actually connect the conjugate classes with irreducible Wepin tensions. So they actually form an invertible square matrix. And well, we're interested in what happened for the periodic groups and also for the modular Wepin tensions. Okay, so I mean, so this actually has appeared actually in several of the previous talks. So I just quickly actually go through this. I just denote by this is the F to be a periodic field. The F brave, this is actually a more geometric object, and this is the completions of the maximum unramified extensions of the F. And this relative field is FP bar. So this actually we can talk about the geometry. And we denote this by I and I brave, the Xuhua He subgroups. This actually are related by this is the Frobenius axiom. And so here, well, for those students who are not so familiar with the periodic groups, and this is a typical example. We can start with the G-N, and the Xuhua wire group is this the Zn semi-direct product with Sn, and the Xuhua. So we have this is all these the entries are in Zp or smaller than Zp. Okay, so now let's actually come back to I cannot say this. We have the several arrows which actually connecting these things. So I want to highlight some of this is non-trivial ones. I put this as a 1, 2, 3, 4. So one is that once you have this is a affine Hecke algebra, you want to get its cocenter. The natural question is that what can we say about the cocenter? Well, so we're interested in the basis and also any element. How do we write this as a linear combination of the basis? And so this is the part 2. Part 2 actually for this is the GIT quotient. So I'm going to talk about actually what is the motivation to introduce this. So this actually comes from the Cocenters classifications of the sigma isocrystals. So this is actually coming from the arithmetic geometry. And when you actually go from the affine Schubert variety, it goes to this is the Newton strata. And if you look at the fibers, this is also some very interesting subject to study, namely the affine Deligne-Lussig varieties and affine Lussig varieties. So the affine Deligne-Lussig varieties actually has been mentioned in yesterday's talk by Xingwen, and so also there's the similar analog, but actually with actually more complicated one is the affine Lussig variety, and also the part 4. Part 4 is also quite interesting. It connects the algebra with the geometry, so it's actually connecting this class polynomials, which is with the algebraic structure with affine Deligne-Lussig varieties and affine Lussig varieties with this geometric structure. Okay. So the basis of the cocenter. Well, we know that for the group algebra, if you have the two elements in the same conjugacy class, they have the same image in the cocenter. But this is not the case for the Hecke algebra. There's some deformation which makes the things complicated. But however, there is some combinatorial result, which actually I proved joint with Xuhua He. Basically says that from any element, we can actually do this by simple conjugation. Each time, weakly decrease the length until it reaches a minimal length element. And also, two minimal length elements, they are strongly conjugate in the sense of conjugation in the Boyd group. So this actually, as a consequence, tells that the image of the element for the minimal length representative, they are the same in the cocenter of the Hecke algebra. And also, if you start with any element, we have a unique polynomial, so that we can write the TW as a linear combination of this is the TO, where all runs from the conjugacy classes of the Xuhua He group, and with the coefficient FWO. We also have the positive property that this is a polynomial of the Q minus 1 with the non-negative coefficients. Okay, so let's come to this is the GIT quotient. So this was actually motivated by Cocenters classifications of the sigma isocrystals. So what Cocenters studied is the start from the PID group or the loop group, and then he associated to each the forbidden twisted conjugacy class the two invariants, the Cocenters map and via the Cocenters map and the Newton map. Any question? Well, so but in fact we can see that this actually indeed comes from the map from the conjugacy classes of the Xuhua He wire group. So so the horizontal arrow is actually surjective. So this actually, the B of G is actually the set of this is the sigma crystals, which also appears in Xingwen's talk yesterday. So we have this actually two invariants, and goes to this pi1 of G, which is discrete, and also the dominant rational characters. And so here we can actually define the JT quotient to be the image. And so this map actually from this is a country class to its JT quotient is not injective, but there is a natural cross section given by some special conjuncing classes, which we call the straight conjuncing classes. And so here actually I gave the example to say you can see that how this is the Newton point is actually calculated. So is that you look at this translation part and also look at these conjugate classes, and this is actually the image is just this condition that, well, you for example, you can have the 1/3. If you have a 1/3, you need to have the 3 of the 1/3. By this is the integrality condition. If you have the 1/2, then you need to have the 2 of the 1/2, and the third one must be an integer. And well, so this actually leads to this is the definitions of the abundant linguistic varieties, which appears as this is the fibers of this arrow labeled 3, the third one. So when you go from the Afan-Schubert goes to this is the Newton strata, those actually stable under the conjugation or Forbin-Twisted conjugation. So we look at this is the intersection of the Afan-Schubert, which is IWI, with the conjugacy class of Forbin-Twisted conjugacy class. So abundant elusive variety describe this is a Forbin-Twisted conjugacy class, and this actually also has the meanings in the arithmetic geometry. So the Afan-Schubert variety it actually corresponds to the Cartwright-Rappaport stratas for the Shimura variety, and the sigma conjugate class corresponds to the Newton stratas of the Shimura varieties. And there are several the major problems: non-emptiness, the dimension, and the enumerations of the irreducible components. And well, so here this is actually the picture from this is the paper by Gertz, Hens, Cartwright, and Ruhmann in the 2006, and they actually discuss about in this is the Afan type G2, what are the dimensions of the corresponding Afan elusive varieties. And due to the time limit, I'm not going to discuss this in details. But I just want to give the impression that this is complicated. Oh, by the way, I have 1 hour, right? Okay, thank you. Yeah, if there's no number, this is empty. Except for this one, this one there is a 0 there. But you are not able to see the 0. Everything is black. That one is the base article. This is actually the Cocenters cells. And so we actually expect that actually. So you can say that actually in the different regions they have the different behavior. So we expect that. In fact, actually, the behavior would eventually be related to the Cocenters cells. And what we can prove is that we can prove this for the lowest two-sided cells. What actually those arithmetic geometry called this is the shrunken wire chamber, and for that we totally understand. But then for the other the two-sided cells, then we still do not understand. Yes. Okay, so the previous we talked about this is the class polynomials and the affine elusive varieties. Let me show you this arrow. This one. So I'm going to say how this is the algebraic part is connected to this the geometrical part. And so what I previously actually proved is that we have this the dimension equal to the degree theorem. Well, basically it says that if you do take into account of the difference between the constructed classes and this is the GIT quotient, and we actually sum up over the fibers, and then the dimensions of the affine elusive varieties is equals to this is the degrees of the class polynomials up to the shift of this number. And well, these numbers in arithmetic geometry, this corresponds to the dimension of the central leaves. And well, it's not only for the dimension, and also the irreducible component is equal to this is the leading coefficient of this is of the class polynomials. And well, then based on this and combined with other techniques, so we're able to prove several important conjectures in arithmetic geometry, including this is the Gertz, Hens, Kautowitz, and Rumans. And this is the non-emptiness pattern, and also Kautowitz-Rappaport conjecture, and the non-emptiness of the Newton strata, and the dimension formula, and the conjecture of Miao-Fen-Cheng and Xing-Wen-Zhu on the irreducible components. JB is the forbidden twisted centralizers of this element B in the loop group. By the way, for the last the Chenzhou conjecture, so actually the two proofs. One is actually by Sanli, the other is by Yihang Zhu and Rongzhou, and also actually joined with me for this conjecture. Okay, now we actually go back to the original motivations for the cocenter. So we try to relate the cocenters with the weapon tensions. And well, if you want to study the periodic groups, we consider the big Hecke algebra, and so this is actually the algebra which are locally constant and compactly supported. And well, so we can actually also form the cocenter, and then we have the natural trace map from the cocenters of the big Hecke algebra to the weapon tensions of the periodic group. And well, the Benson, Delin, and Castan proved in the 1986 that for the complex weapon tension, the cocenter and the wave potential, they actually dual to each other. This is no. Okay, so motivated actually by the previous consideration, I realized that in fact the Newton point is actually is important. Then I introduced this is Newton stratifications for the loop group. So this is actually the set theoretical decomposition. Is that if you have the periodic group G of F, then this is a disjoint unions of what I call this the Newton strata. The definition is that we take this is the periodic group, then we intersect with the forbidden twisted conjugate classes of the loop group. And then we know that each of these is actually stable under the conjugations of the periodic group. And this is also a discrete decomposition. Each Newton strata is locally closed. New here means this is a Newton point. Newton point, and so I have the, oops. Sorry. The Newton point is something like this. For example, for the GO3, you think about this actually a sequence of the rational numbers satisfy this integrality condition. So this is actually a discrete set. Okay, so well, why we care about this is Newton stratification. Well, instead of thinking about decomposition into a conjugacy classes, one reason is that when we actually study the wave potential of the periodic groups, we want to have this is a smooth and irreducible, and this is smooth condition, which actually leads to that for any functions on the periodic group, it must be locally constant. So which means that if you actually contain a point, you have a support on a point, then it also support on the small neighborhood of the point. And which means that we are not be able to actually single a conjugacy class out from the others. And so, but this one, each of this is the Newton strata. Actually, this is actually each of this contains a small open neighborhood, and also this is a discrete, and so this actually leads to a nice decompositions for the Hecke algebra and its cocenter. And also, we can see that this decomposition is compatible with a nice level structure. And this actually also leads to some finiteness result when we actually restrict to each the Newton strata. And so, as a consequence, actually, we have actually several nice applications to the wave potentials of the periodic groups. For example, the House conjecture on the finiteness of the invariant distributions restrict to any compact set. And also this is the trace partner winner, and now we are able to do this for the mod L, when L does not divide the order of the finite wire group. And also the abstract Sabog principle is for the mod L, when L is not equal to P. And also actually my collaborator for various of this development, the Chiptaro, he also actually uses these ideas to show that the types preserve the unitarity. Okay, so I have roughly the 20 minutes. So I'm going to actually talk about some recent works towards the categorification. So in the beginning, we actually mentioned actually one of the motivations for the Hecke algebra is that this is the endomorphisms of the functions on the flags. And in fact, we can actually upgrade this to the Hecke category. And the final Hecke category, this is actually the derived category of the constructible sheaves. And this is on this quotient stack, G quotient by B on both sides. So Hecke algebra is the functions on this quotient stack. And this is the Hecke category is the constructible sheaves on this. And well, the sheaves could mean the D modules when the group is defined over complex numbers, or the Étale constructible sheaves when G is actually defined in positive characteristic. And well, so this is actually one of the most beautiful thing which I learned from George while a student in MIT, something like the 20 years ago. And is that so George wants to actually give a geometrical realizations of the characters of the representations of finite group Lie type, and he also wants this actually to work over complex numbers. And this is actually a really beautiful geometrical construction. Let me actually first introduce the notation. Well, why done this as a fraction? This actually, I just mean the conjugation action. And well, if actually do this the slash on the left and the right, it means that we're forcing out the group action on the left or on the right. So on the right hand, this is actually the G quotient by G. This is the quotient stack of the reductive group by its conjugation action. And in the middle, this is not the flag. Flag is G over B. B is on the right. So this is actually G. So for this one, this is actually quotient out by B by the conjugation. And so on this side, this is the universal finite Hecke category. And well, so how this is actually related? We take the pull back and take the push forward. So this is the character functor, and the definition of the character sheaves. The category of the character sheaf is the thick category of the image of this character functor. Well, this is actually many actually beautiful properties. I just only list a few. First is that the character sheaves provide the geometrical realizations of the characters of the representation of the finite group Lie type, and also the derived categories of the character sheaves is equivalent to this the categorical trace or categorical cocenter, and also categorical centers of the finite Hecke category. When we actually goes from the finite to affine, there's a difference between the categorical center and the categorical cocenter. Okay, so and now we actually want to actually move from the finite to the affine. We want to understand what happens for the analog theory for the loop groups. But this one is this quotient stack, and is a very complicated geometric object, and so yesterday's talk, Xinwen actually goes into the details about this. So I just want to point it out that why this is actually complicated. First, this is not an indefinite type. And also, we're going to actually take this as a really large quotient. And actually, some of the situations, related situations, has been studied previously. For example, in this geometrical long line, people are considered about this is a LG quotient by P, where P is a parahoric. So this is the Afan flag, and but this quotient, this parahoric is what they call so-called the Placid group scheme. And the other is that this is a work of the Batir, Kastan, Warshawski. What they consider is this a quotient, say quotient by the loop group. We'll say this is a compact part of the Lie algebra, which is a Placid scheme. But here, I mean, both the numerator and the denominator, they are actually very complicated. Well, anyway, I would say that actually, but actually, thanks to the thanks to this is a Newton stratification that we can get some controls of this. Well, so this actually took me actually many years to finally figure this out. First, I did this on the levels for these are set theoretical levels for the periodic groups. So we have this is a Newton decomposition, the set theoretical Newton decomposition for the periodic groups, and we have already seen that it has many applications to the big Hecke algebras and to the representations of the periodic groups. And later, joined with Nier, we have this set theoretical interpretations for the loop groups. But this now consider this as the intermediate step, and the final version is actually this is the skin theoretical levels on for the loop groups. So this is actually joined with Xinwen Zhu and Eliado. So each of this is a Newton strata is the perfectly finite presented locally closed subscheme of this is a loop groups scheme, and we have this is a nice decomposition. Also, we have this is the Clore relations. This can also be regarded as a generalizations of the Cocenters conjecture, and this is the whole loop group is actually regarded as a co-limit of the Newton strata. So built from this, and also modular the complicated the shift theory, which appeared in this is the 400-page paper of the Xinwen, and so and now we can talk about the derived category, the derived categories of the constructible shifts on this quotient stack, and also on this the Newton strata. So then this actually defines a Newton stratification on the categorical level, and so this actually also we obtain this is a so-called this is a semi orthogonal decompositions of this the category. Since I still have time, so maybe actually I mentioned some difference between this construction for this is the conjugation action and the forbidden twisted conjugation action, which appeared in Xinwen's talk yesterday. So here, if you consider about the fibers, if you think about the sigma conjugation action, the fibers. So the fibers actually we related to this one are affine Linguistic varieties, which is complicated, but we have a fairly good understanding. But here, if you think about the conjugation axiom, and so what appears in this the fibers of this is the affine Lusky variety, which is actually even more complicated. And so I have the several papers on this, and well, philosophically, the affine Lusky fiber is the affine Lustig, then plus the affine Spinger fibers. To combine the two complicated objects together, it's really complicated, and so this and well, obviously one of the reasons why this is actually more complicated is that for the Frobenius conjugation action and for the finite type reductive group, we have the long theorem. We only have the one Frobenius twisted conjugacy classes. But for the ordinary conjugacy classes, it's very complicated. And so George yesterday gave a talk on these stratifications. And of this is the finite type reductive group. And this is actually much more complicated than the Frobenius twisted conjugation action. And well, anyway, put the long story short. Okay, so so we have this is a Newton decompositions. For this is a derived categories on this is a whole quotient stack. But now, if we actually restrict to this is the affine Hecke category, so we can consider about this categorical cocenter. And so we can actually relate this to this derived category on this quotient stack. View Lustig's character functor. And so we showed that this one is actually fully faithful and admits the white adjoint. And moreover, this one admits the the Newton stratification, and they're actually a similar result, slightly weaker version, but by totally different method is actually is typed by Penghui Li, Nadler, and Zhui Yun. So they actually used this actually to solve this is long-standing problems on the wins of the invariant functions on the commuting schemes. Okay, so I still have a few minutes, and let me explain more about this. So what we can do is that actually for this, I write this as a affine Hecke category, but in fact we can also take into account of the characters on this is the finite torus, and so this actually leads to a slightly larger Hecke category. And if you look at this categorical cocenter, then we can actually define its image inside here. So what we actually obtained is what is expected to be this is the depth 0 character shifts on the loop groups, and also this is actually what we actually writing at the moment, and is that we have this Newton stratification, but what we can say is that each Newton strata, so each of this the Newton strata is in fact the Newton strata for the Newton point equal to 1, corresponding to some inner forms of some Levy subgroup. And this, and also this actually means that essentially we only need to consider about this is the Newton point equal to 1. This is this particular compact part of the loop group, and these Levy subgroups for all this is the inner forms, and we actually putting this actually together, so we get this is the large category, and also we have this is the compatibilities between this is the pull back and the push forward, and so if you have the so if you have this is the depth 0 character shifts on here, if we can actually pull back to each Newton strata, and then we actually take the push forward, the star push forward or shrink push forward, then we actually still get this the depth 0 character shifts. So this is actually the compatibility with the depths. Okay, so let's see. This is actually this is the topic of my talk actually, which connects the algebra, combinatorics, and geometry. And thank you very much.
Thank you. Questions?
Can you say a bit more about this compatibility between depths? Is there some functor being adjointable or something like what goes into this argument?
Talk about this one, all right?
Yeah.
Well, so I would say that actually, so the depth 0. Let's actually go back to maybe I think I still have some time, right? Yeah, maybe I explain more on this. And so in the George's definition of character shifts, there's actually two definitions. One is which I outlined here using the character functors of the Hecke category. The other one is the admissible complex. So he defines some stratas and some classical local systems on the stratas, and then take the IC. And so here, for the depth 0 character shifts, what you can think of is that we can start start from some Levy, and we think about this admissible complex on that Levy. So then we actually do this is the parabolic induction. Well, we first actually lift this actually to the parabolic, and then we use this is parabolic induction. So then we get some shifts on the whole loop group. So this is actually one definition, which actually coming from something actually locally. The other is that we just using this definition, which is something global. So you can see that actually these two definitions, they actually are compatible, because essentially to George that actually this actually locally these two definitions are compatible, and also we have this is a Newton decomposition, which we can restrict to each Newton stratas, and also this is a Hecke category is actually stable under this is the pull back and the push forward. But if you start from some admissible complex, you have this define this actually locally. If you want to prove directly that is push forward is a character shift of the depth 0, then that is very difficult. This is also mentioned by Xingwen yesterday. Some similar phenomena. Also, I would like to say that actually this is the decompositions of this is the G or maybe some other varieties into the smaller pieces stable under conjugation action, and you try to define the character shifts locally and on each strata, and define it locally and to say they're compatible. I first actually learned this from George when he actually has several papers on this parabolic character shifts. And this is actually a similar phenomenon.
More questions?
So for in case of unipotent, I had some paper almost characters.
Yeah, yes.
So is that compatible with what you're doing here? That was that special only unipotent, not all depth zero, just unipotent.
Unipotent.
I had some proposal for what should be the character shapes.
Yeah, should be, but we haven't checked that.
You haven't checked that. Yeah. But it looks similar to what
you
said.
Similar, yes.
Admissible. It looked like you said admissible.
Right.
So that's the same method.
Right.
Okay.
More questions? No. Let's speaker again.
Thank you.